Hello, everyone. My name is Avni Saxena, and today I'm going to be presenting the research of the QCY group. Our project is called The Effects of Color and Image Manipulation on Cervical Spine X-rays. So we're trying to solve a medical problem using artificial intelligence. Specifically, we want to help detect a neck condition called cervical spondylosis more accurately by teaching a computer how to read those X-ray images. So, for a quick overview abstract of what we're doing, cervical spondylosis is a condition that affects the bones and the joints in your neck as you get older. And it can cause pain, stiffness, or even nerve issues. But on an x-ray, especially in the earlier stages, it's very hard for doctors to spot. Our goal is to see if we could use deep learning, which is a type of artificial intelligence, to recognize this condition automatically. We also tested whether editing the x-ray images before showing them to the AI would also improve accuracy. The end result was that it did work. With the right edits. Our model was actually able to correctly identify the condition almost 96% of the time. So let's take a moment to understand what cervical spondylosis actually is. The cervical spine is the top part of your backbone, so basically your neck. And as we age, the bones and the soft tissues in this part of the body can start to wear down. And this is called cervical spondylosis. Again, it leads to this pain, reduced movement, nerve problems, and it's basically this age-related wear and tear of the neck bones and discs, which are the little cushions between the bones. It is actually very common. About 50% of people over the age of 40 have it, and 85% of people over the age of 60 have it. The tricky part is that on an x-ray, these changes can be very subtle. If you look at the diagram on the right here, these issues might just look like a small bump or a spacing issue, so human doctors' eyes can easily miss it, especially if the image quality isn't great. And this manual diagnosis is very time intensive and very subjective. So why do we want to use deep learning to solve this problem? Let's talk about the technology. We used a method called deep learning, specifically a convolutional neural network, or a CNN, as I'll refer to it. Think of a CNN as like a very observant student. So it's learning by looking at a bunch of pictures and figuring out what makes it different. So think of it like this. If you look at the image on the right here, let's say we're training a CNN to tell fruits apart. So like apples, lemons, pears. So first it's going to look at thousands of labeled fruit pictures, and it's going to learn the small features first, like the curved lines, the stems, the texture. And then the more deeper layers are going to start to combine those pieces. So it's going to learn like, okay, if it's curved and shiny and red, then it's an apple. So that's exactly what we did. Instead of fruit, we gave the model x-rays and we taught it, here's what a healthy spine looks like versus one with spondylosis. And then whenever we give it a new image, it can tell us if it's most similar to a healthy spine or most similar to one with spondylosis. So we have that input where it's identifying the basic features. Then we go through all these layers so that we can eventually reach an output of healthy or unhealthy. Now, this kind of technology has been previously used in brain tumors and in chest scans and a lot of medical areas, but not so much on spinal cord or neck injuries and diseases, which is why we specifically wanted to innovate here, since these problems really do harm a lot of people. So we started using these CNNs, and the immediate problem that we ran into is that cervical spine x-rays vary in quality. So some of them have like labels or markings, some of them are bright or dark in different areas, or sometimes the spine is off center, or parts of the skull, like you can see in the image on the right here, are still showing. And that kind of noise makes it really hard for the model to focus on just the spine. So we had a hypothesis. If we clean up the images first, especially by cropping the image so that the spine is centered and clear, then we think the model will perform better. We tested that idea by creating different versions of the data set, each with a different kind of pre-processing, and I'll explain that in a moment. But first, let's talk about our data set and what the problem was with it. We used a public data set called the Cervical Spine X-ray Atlas, or the CXSA. This contains about 4,963 cervical X-ray scans, and these were all either labeled as healthy or as diseased. But here was the big issue. Only 181 of these images actually showed healthy spines, which is less than 4% of the entire data set. So that's like if you showed a student thousands of pictures of sick spines and then like barely any healthy ones, it's not really going to learn how to recognize what healthy actually looks like. So this imbalance made it really easy for the model to just guess diseased for everything and still be mostly right because it's thinking, well, 97, 98% of the time the spine is diseased, so it's just going to guess diseased every single time. So along with that, we also did correct some of the mislabeled files and removed images with missing data. But basically, to account for the fact that such a small amount of our images in the data set were from healthy spines, we used oversampling techniques like SMOTE. So SMOTE stands for Synthetic Minority Oversampling Technique, if I'm getting that right. And what it does is it looks at the few healthy X-rays that we do have over here, and then it creates new, like, fake healthy images by blending parts of real ones. So these new images aren't exact copies, they're just realistic variations that give the model more to learn from. It's kind of like showing a student more examples by drawing different versions of the same shape from multiple different angles. So the reason we did this is that it helps us balance the data so that the model actually has a fair chance to learn both healthy and disease patterns and then has more accuracy overall. Now, earlier I talked about our pre-processing techniques. So what we did was we created 6 different versions of the dataset to test different editing styles. So first was just the original with no edits, and then we did cropped, so cropped it closer to the spine. We did wide cropped, which was even more spine with like a margin. Color enhanced, where we adjusted the brightness and the contrast. And if you go ahead and look over here, you can see that sometimes the spinal x-rays are white on black versus sometimes being black on white, right? So that's what kind of confuses the model. So that's why we tried testing different color enhancements. And then we also did combinations, so cropped and color enhanced, wide cropped and color enhanced, and we tested all of these through our model to see what kind of pre-processing will give us the most optimal end results. So we have these pre-processed images. Now let's talk about what we're actually putting them into. We tested 2 deep learning models. So the first was VGG19. Back to the same student analogy. This is like a student that's learning very step by step through a very strict routine. It has 19 layers, so that's like each of the filters that I talked about earlier, and it works by stacking these simple building blocks. It's very good at spotting like more basic features, but it doesn't remember context very well. So that brings us to ResNet 50. This one is a little bit more advanced. It's like if the student not only is learning step by step, but also writing notes and referring back to those notes. It has 50 layers, so a lot more, and it includes shortcut connections that help the model learn better without forgetting earlier steps. We did find that ResNet 50 was a lot more accurate and more flexible, so we ended up using it for the rest of testing. Okay, and then augmentation and training. So we wanted our model to learn how to recognize spines from different angles. Because remember, these real-world x-rays are from different angles, they're not all standardized. So the model should be able to handle that. So for that, we use data augmentation. So we took the images that we had and we flipped them like left, right, or up and down, or we rotated them a little bit. Stuff like that kind of gave our model more variety to actually learn from. And we resized all images to a standard size and split our data set into 75% of it for training, and then so that we could teach the model, and then the other 25% for testing so we could see how well the model learned. During training, we used 2 key things: a loss function, which tells the model how wrong it was and by how much. So think of it like giving the student a grade on each answer. And an optimizer, which helps the model fix its mistakes each time it gets something wrong. So like like a tutor guiding the student to improve after each question. So we trained for 30 cycles or epochs, that's what they're called, and we adjusted the model each time. So you can kind of see like the full image of what we did over here. So we start with the original, we do a center crop to make sure it's pretty standardized. We do all of that pre-processing stuff, and then we did make sure they're all 224 by 224 just for standardization. And then we do our augmentation with all those tilts, flips, rotates, whatever. And then we run it through our deep neural network, in this case ResNet 50, and then it gives us the classification of either healthy or diseased. So let's talk about our results. Here's what we found. The original data set, when we ran it through our models, gave us 94.19% accuracy. But when we used wide cropping or color enhancement, those each improved the accuracy up to about 95.73%. But surprisingly, when we used both at once, that actually ended up slightly lowering the accuracy. So this told us that some editing was helpful, but too much could actually end up erasing those more important details. You can see that wide cropping is what gave us the best balance between being correct and also not missing anything. So we have these like statistics and we took a look at all these results here. But we did want to make sure that the improvements weren't just from luck, like just by chance. So we used something called a statistical test. In this case, we used a z-test. This test compares two results and it tells us how confident we can be that the difference is actually real. If the number it gives, called the p-value, is less than 0.05, then that means that there's less than a 5% chance that the results were random. So both wide cropping and color enhancement passed that test, so we know they made a real difference. But the combined version didn't, which means that it wasn't clearly better than just doing one thing. So let's talk about our limitations when we were doing this. Even after smoke, our data was still a little bit unbalanced because we have thousands of disease pictures versus smoke can really only do so much augmentation to make that balance. We also only tested two models, VGG16 and ResNet 50. Other new models might work better. And then also our models were classical, which means that they process data one piece at a time, which is often slower and less efficient than the potential of quantum alternatives, which I'll talk about in a second. Now, for our future work, we definitely want to try EfficientNet. That's just a model that's more accurate and fast. We want to test ensemble models, basically using multiple models and combining their results as if it's like a team of experts. And then, most importantly and grandly, we want to explore quantum machine learning, which is a completely different and exciting area. The reason that this is so impactful, that I feel that our project is really so interesting, is that we're able to hopefully one day deploy these types of models in clinical decision tools that really makes that real world impact. So I've alluded to quantum computing. Let's talk about what that actually means. So here's a quick intro to quantum computing. Traditional computers use bits, so that's either 0 or 1. Quantum computers use qubits, which can be 0, 1, or both at the same time. This is called superposition. So this allows quantum models to analyze many possibilities at one time. It's like you're able to look at an image from multiple angles instantly. They can also take advantage of what's called entanglement, where qubits are connected and share information even if they're far apart. And what this means is that quantum AI could process medical images much faster and find patterns that classical models can't. We really do think that this is the future of medical image diagnosis because it's able to look at these complex image patterns like spinal misalignments, which are very nitpicky, very specific things. And we hope that we can bring our accuracy even further up by using quantum computing in the future. And that's really the grand goal that we have. So thank you so much for listening. For some acknowledgements, we want to thank, of course, ASDRP and Dr. McMahon for all the support. Also, shout out to the QCX research group. So QCX is doing similar work as us, except they're looking at the brain and the skull. And so we really think that they've been such a help to us in our collaborations and as we've been going throughout this whole process. So thank you to them. If anyone has any questions, please let me know. I don't know if I can see the Zoom meeting. Yeah. Um, show meeting. Okay, I got it. Yeah. Does anybody have any questions?